Welcome everyone. So obviously we expect many connections between algebraic geometry and statistical learning theory. We've discussed some of them, the role of the log canonical threshold, resolution of singularities, but there are others which are either completely undeveloped or latent, and today I want to talk about one of those which, as far as I know, hasn't been raised in connection with Watanabe's work. Maybe there's some connection between jet schemes and algebraic statistics, which is a broader area in which Watanabe's work could be sat, the application of commutative algebra and algebraic geometry to statistics. The broader area of algebraic statistics is Watanabe has a sort of different set of concerns to some of the rest of that field. So jet schemes may have come up in that connection. A brief search didn't turn up anything. But for reasons I may not get time to explain today, but may come back to, I do think it probably plays an important role in some of the questions that we worry about. So just to set the scene, the usual setup is that we're given a statistical model, PQ var phi, I guess phi. The KL divergence K. Suppose we've succeeded in finding some equivalent polynomial H. Then, as we know, to compute various asymptotic quantities to do with the learning process of this statistical model, we want to perform a resolution of singularities, or what in the algebra geometric literature is usually called an embedded resolution. Of the set of true parameters inside W. So W0 is the vanishing set of H, equivalently the vanishing set of K. And the embedded resolution looks like this, or an embedded resolution, I should say. It's quite important. There's a commutative diagram like this. G is the resolution. It's an embedded resolution because the pre-image of W0 is in normal crossing form. G is birational and proper. It's an isomorphism outside of W0, so the complement of U0 and U and W0 and W are isomorphic, and that's what we're looking for. Now, as we've discussed many times, G may be hard to find. There's a second problem which we haven't spent a lot of time talking about. If you've read through the Grey Book, you know that it's not that the embedded resolution, well, it's not that an embedded resolution is unique. There are many resolutions, embedded resolutions, which are in some essential way different. Now, you can compute the RLCT using any of them. The RLCT is an invariant. It's independent of the choice of resolution. So you just find one. Hence why you have these ad hoc procedures in the papers and the books to find these blow-ups in order to compute the resolution. You do whatever ad hoc set of choices you want. You'll get a resolution that depends on your choices, but you don't care because the RLCT is independent of those choices. But we have started discussing trying to infer more information from the resolution than just these numbers, right? The K's and the H's and the RLCT. And the status of that is left a little unclear if the structure of U and U0 depends on the choice of resolution. Okay, so there may be information in G or U which is not intrinsic to W0. It's just some artifact of our choices. It isn't actually telling us anything about the singularities or the learning machine. Alright, well, what's an example of a situation where we care about more than just this birational invariant, the RLCT? Well, for example, in the abstraction seminar, we've started trying to investigate some conjectural relationship or dictionary which links abstractions or concepts or perhaps some generalization of sufficient statistics or principal components, whatever you want to call them, to to exceptional divisors of the resolution. We haven't formally said what exceptional divisors mean in these seminars, I think, but just to draw a picture, U0 is in normal crossing form, so it will look something like this in higher dimensions. You can pull it apart so that locally it looks like vanishing of coordinate functions. And the irreducible components, so the 1, 2, 3, 4 lines that I've drawn there, are the irreducible components of the exceptional divisor of the resolution. So the exceptional divisor is just the pre-image of W0 under the resolution map. Well, that can't be right, if what I just warned you about is true. If the structure of U, G, and U0 depends on the choices you make in the resolution, that can't really be anything important, right? It can't be to do with the statistical problem. It's just to do with the way you chose the resolution. So we can't literally mean take any resolution of singularities and take the irreducible components of the exceptional divisor. We don't believe that any irreducible component is somehow important. So what we want are somehow the irreducible components that are essential. That is, the irreducible components such that no matter which resolution you pick, somehow you'll see that component in the other resolution. So it's one has to, it's not clear exactly how to formulate this correctly, but hopefully at a conceptual level it makes sense that you want the irreducible components that show up no matter which choices you make in the blowing up process, for example. Okay, so I'm not going to define what an essential irreducible component is. This is kind of setting up the motivation for the theory of jet schemes. So Nash was thinking exactly about this problem that we just discussed back in the 60s. Namely the lack of canonicity of the irreducible components of the exceptional divisor of a general resolution. And in this connection he introduced jet schemes. So I'll state a theorem of Nash without really explaining all the parts in it, but I hope the content still is clear. Okay, so what did Nash do? Well, it's a little awkward because I'm going to state a version which is not about embedded resolutions. So let me back up a bit. For a variety X, with resolution of singularities G. Okay, so this is a bit of a different situation to the previous board, right? But at some level, the content transfers over. So for a variety X with resolution of singularities G, there's some other construction you can make called the arc scheme. And an injective map from the essential exceptional divisors of the resolution to the irreducible components of the preimage under pi of the singular locus of X. And the Nash problem is, when is this a bijection? It isn't always a bijection. It's a bijection for toric varieties and in some other cases. I don't really want to get into that, although maybe it's interesting later. For the present purposes, let's just pretend it's a bijection. So what does this theorem say? It says that if you want to just get the essential components, the essential exceptional divisors from a resolution of singularities, what you ought to do is study, instead of the resolution, this arc scheme. The arc scheme is not a resolution of singularities, it's some other object, but it contains somehow just the essential information that's common to all the resolutions, at least some. Okay, so that's the idea behind the jet scheme. There's no jet schemes here, I guess, as it stands. So x infinity is an inverse limit of xn's. The xn's are called this is the nth jet scheme. Right, so the arc scheme, I misspoke before, the arc scheme knows the essential exceptional divisors of any resolution of singularities. The arc scheme is kind of approximated by some tower of finite truncations, which are these jet schemes. Okay. So the question I want to pose, and I think this is an interesting research direction, I mentioned it in the open problems session. Okay, so loosely speaking, we know what an arc is, right? So an arc on a circle is some segment of the circle. An arc is, in general, if you're on a manifold, an arc through a point sort of means an infinitesimal piece of a smooth path, right? So that's the kind of object that an arc is. So what kind of arcs do we expect to encounter in a learning machine? Well, imagine that you're doing gradient descent or stochastic gradient descent near W0. Well, the idea is that you start somewhere and you're going to end up near this most singular point. The idea is that in some sense, I don't know how to make precise, but which is clearly true, SGD near here, which you could think of as gradient descent with respect to a perturbed KL divergence, right? So nearby in function space, you take some Kn, And if you do you look at the vector field associated to that. So degenerating Kn to K is a little bit like taking a jet scheme in a family. Now that isn't quite going to work, but you can, by thinking about those kinds of things, get some way to convincing yourself that probably the jet scheme of W0 contains a bit of information about what SGD near W0 sees and its dynamics. So that's an interesting direction to explore further, and that's what I have in mind for this question. I don't know how to make that precise yet. Okay, so that's the high-level motivation. I'll pause here for questions and then get into some more precise material.
Hey, maybe I missed it, but what's the etymology of jet schemes? And arc schemes. I understand the arc part now, but I also don't know what a scheme is.
Yeah, good question. So for scheme, you should just read algebraic variety.
Okay.
So, for example, the vanishing of H inside R to the D. So that object's an algebraic variety, as you know, and an algebraic variety is a scheme. So a scheme isn't just a topological space, it's a topological space together with some collection of functions on it. Essentially, to form a scheme from the polynomial h, you're remembering the set of zeros of h, but essentially also the function h itself. So it's some kind of slightly complicated mathematical object which subsumes the notion of an algebraic variety. Jets. Yeah, jets I'm going to explain. So you should think of the following dictionary as 0 jet is just a point. A 1 jet is a tangent vector. A 2 jet is, well, you don't have any other word for that. It's what you get when you remember the behavior of some object near a point up to second order rather than just first order. So jets are the one way of generalizing tangent vectors.
Cool.
Other questions?
That makes sense.
Can't understand you, sorry.
Okay.
You can always type, sorry. All right. Okay, so that was very high level. I'm still not going to get to precise details because it's a bit tricky to obviously introduce stuff to do with schemes when I don't want to spend several months introducing the theory of schemes properly. So I'll try and...
Dan, sorry.
Yeah.
Ben's question in the chat is, what's a reverse limit?
Oh, an inverse limit. Yeah, I don't want to answer that question. Yeah, it just means a way of taking some finite objects and taking their limit. So there's a notion of limit of algebraic varieties. So just as you can take a limit of real numbers or functions, you can take a limit of algebraic varieties. It's a relatively sophisticated notion, though. So for the moment, just imagine if I say 0 jet, 1 jet, 2 jet, ... where the ... ends is the arc space. It's the limit of all these finite things. Sorry, I can't be more helpful than that.
Would it be appropriate to think about Taylor expansions?
Yeah, that's exactly right.
Cool.
Yeah. So the discussion about, as you'll see, the discussion about jet schemes is really just packaging for Taylor series expansions of functions. That's essentially what we're going to be discussing. So that's like it boils down to something that isn't that sophisticated.
Can I ask a question?
Yeah.
For this jet scheme here, if say x is variety is a if we look at x is a variety, then we look at this this arc space, then is that the you take the completion of the algebra corresponds to that variety?
Yeah, that's almost right. Yeah, so you're going to the one jets and two jets come from taking quotients of polynomial rings by t squared and t cubed, respectively.
Yes.
And arcs basically come from taking the power series ring itself, which is the inverse limit of all those quotients. That's right. But where you exactly put the completion and so on, I mean, it's a little bit, it's not completely straightforward, but essentially it's just a completion at the level of the algebra, yeah.
Okay.
All right, so let me pick up that last point about 0 jet, 1 jet, 2 jet, and so on, and sort of motivate how we're going to define jet schemes. Basically, the word scheme will just disappear and turn into algebra at various points at any time that we actually compute anything. So I want you to think about the category of schemes over K. So just think about algebraic varieties over, and K for you, for us is R. So in the category of schemes over K, well, there are special objects which are not in fact varieties. So they live in this, they're outside the subcategory of the algebraic varieties. At least in the, they're not irreducible. It depends whether or not you believe varieties are irreducible. So, okay, they're not like the objects that we've usually been considering, I suppose. I'm calling them point with a subscript, and I want you to think about 0 as being like an actual point, like a Platonic point. And 1 is a Platonic tangent vector. I'm actually going to define these in a second. This is something that is like more information than a tangent vector. So if you know what spec is, that's what this thing is. It's the spectrum of this ring over K. Now, I don't expect that to mean much to you. I'll explain. I'll make the connection between this algebra and jets very explicit, hopefully by the end of today. But for the moment, just in case you know what the spectrum is, I don't want to pretend like this is mysterious. Okay. Now, I want you to imagine that the category of schemes has exponentials. That is, that given schemes x and y, that you could form a scheme, sort of an algebraic variety kind of object, whose points are suitable maps from y to x. In fact, this doesn't exist in the category of schemes. If you know about topos theory, such exponentials exist in the Zariski topos. That's outside the scope of these discussions. It doesn't matter, but it's important to have the idea that this is what you're doing, even though it takes more sophisticated techniques to actually formally do it. But in some sense, you can do this. You can take two schemes and you can take the sort of function space from one to the other. Okay. Well, what happens when you take the function space from the Platonic point to any scheme X? We just get X, right? The scheme of maps from a point to a space is just the space itself. If you take x to the power of the Platonic tangent vector, what do you think you get? What is the space that parameterizes all the ways to stick a tangent vector onto x? It has another name.
The risk of embarrassing myself, is it a vector bundle?
Yeah, it's the tangent bundle, that's right.
Okay.
The tangent bundle is another scheme whose points are pairs consisting of points on x and tangent vectors at those points. Okay, now we can keep going, right? We don't have another way of thinking about that. That's a way of sticking a little Platonic order 2 jet into x. But xn, the nth jet scheme, is by definition x to the power of the Platonic nth jet. Okay, so that means that x0 is just x, x1, the one jet scheme of x, is just the tangent bundle, and then so on. Okay, well, that isn't really a definition, because I told you that actually this exponentiation operation doesn't really make sense in schemes. You need some fancy thing to do it this way. But, okay, this is the correct way of thinking about it, and then we can find another way of saying the same thing, which I'm about to explain to you, and then turn detailed enough that we'll actually compute a jet scheme of a surface in maybe 10 minutes. All right. Okay, so let me move on to the next board and try and turn this into a definition that's a little more concrete. Hopefully you get the idea of what it's supposed to do. Okay. Consider the following calculation. I'm going to put calculation in scare quotes for the reasons I just explained. This actually doesn't take place inside the category of schemes because the exponential doesn't exist there. But that won't stop us. All right, so suppose you take some scheme Z. Then the home space in the category of schemes over K from Z to this nth jet scheme. Well, if you take functions from Z into a function space, then there's an adjunction which says that that is this. It's just currying. And if Z is affine, and we take this Platonic n-jet thing to be, as I said, the spectrum of this ring, then that's spec A, this product is over K, with spec of this thing, comma X, that's a tensor over K with this. That's just AT modulo T to the n plus 1. And finally, if you take Homs out of spec, right, so okay, so the upshot here is that, well, a closed point of this object here, so that means taking Z to be spec K, is, well, if I take A to be K in that final line, it's a morphism of schemes. Like that. And if X itself is affine, this is the same as a morphism of algebras. The other way, from R to KT modulo T to the n plus 1. Okay, so I apologize for invoking schemes and talking about all of that. It's actually not, we haven't covered that kind of material in the seminar series, and I'm not assuming you know it, but it's part of the justification for why the notion of an n-jet, so an n-jet, algebraically speaking, is the same thing as a morphism of k-algebras from some ring to this object kt modulo T to the n plus 1. That's one way of motivating it. I'm now going to switch gears entirely and motivate it from the point of view of a Taylor series expansion. So this is the kind of high-powered derivation of why this is the right kind of object. But we'll see it from a few different points of view. Okay, so, well, the calculations were in scare quotes, right? So this actually isn't a definition of the jet scheme, but what you can do is you can prove that this functor is representable. So theorem, so this is actually how you prove the jet scheme exists. So the theorem, the functor which sends a scheme Z to the right-hand side of that first line there, the set of morphisms of schemes from this product to X is representable, i.e. let's just say X finite type. It exists in general, but there is a scheme Xn such that which does the job and makes that calculation an actual calculation, not just a scare quote calculation. Alright, so this is how algebraic geometry works at some level. You kind of fly by the seat of your pants and invent an object, then you construct a functor, which if it had a if it was representable, would be represented by your object, then you prove it's representable, and there you have it. Okay, so this is where the jet scheme comes from and how it's proved to exist. Okay, now I want to put a line under that and switch gears, as I said, and talk about Taylor series expansions. Well, yeah, maybe I'll do an example first. Are there any questions? Okay, I want to do the example so you see in practice how this is kind of how you would actually find x sub n. Okay, so saying x equals spec this. Another way of saying that is that x is the vanishing set of f inside k to the 3. Just viewed as a scheme rather than as just a set of points. So this object vf is what x is. So what is a 2-jet, or just an m-jet? An m-jet to x is... Okay, so you're imagining this surface sitting inside k cubed. What is an m-jet? Well, we know a 0-jet is just a point of x. A 1-jet is a tangent vector. 2-jet is something. Okay, well, by the prescription that I've just introduced, which by definition, an m-jet to x is a k-algebra homomorphism, let me call it gamma star, from the ring to kt modulo t to the m plus 1. All right. Well, how do we classify all such k-algebra homomorphisms? Well, remember that a k-algebra homomorphism out of a quotient of a polynomial ring is, so we have the quotient kxyz goes to kxyz modulo f, and we've got our gamma star. A k-algebra homomorphism out of the polynomial ring is completely determined by what it does to x, y, and z. So the data in gamma star is the image of x, y, and z, and then there's some constraint. Okay, so the data of gamma star is what it does to x. We call that xt. And that's something in kt modulo t to the m plus 1, right? Which is k plus kt plus dot 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 kt to the m. So the coefficients are some scalars. So let me call them x0, x1 through x sub m. Similarly with y and z. Okay. Now what's the constraint? Well, when you feed x, y, and z into gamma star, okay, so you get these things here, but it has to factor through the quotient by f, which is to say that when you feed in f to gamma star, you have to get 0. So the constraint is that when you substitute xt for x, which is what it means to evaluate gamma star on f, and yt for y, and zt for z, you have to get 0 modulo t to the m plus 1. Okay, but imagine substituting x, t, y, t, and z, t into f some polynomial in x, y, and z. All right, so you have some brackets, and you expand all the brackets, and what you've got is a polynomial in t. Right? So you've got a constant term, f0, you've got a linear term, and you've got all the way up to the mth term. And if you think about it in terms of the expression, it's a little imprecise here because xi, yi, and zi are really just scalars, right? This thing here belongs to kt modulo t to the m plus 1. So the xi, yi's, and zi's are just scalars. But if you think about the expression on the page, when you expand out all those brackets, the fi's or fj's will be, in the way you wrote them down on the page, some functions of the xi's, the yi's, and the zi's. I hope that makes sense. And then I suppose you have higher terms here, but we don't care about those. So this equation, this constraint, tells you that f0, f1 through fm vanish. Right? Okay, so these are actually the equations of the mth jet scheme. So the mth jet scheme of X is the space which has these xi's yi's and zi's as coordinates, and these f0 through fm's as equations. Why? Well, that space exactly parameterizes gamma stars, right? To take a point, so what is a point of this space? Well, it's to take a point in k to the 3m, that is assignments of scalars to these symbols xi, yi, and zi. That is the data of these three objects, subject to a constraint. The constraint is, on the right-hand board, that these equations all vanish, but that is what we agreed is exactly the constraint for this. I mean, giving me some data like this just tells me specifying xt, yt, and zt just gives me a k-algebra homomorphism like that. To get it to factor through the quotient, I need to know that it satisfies some constraint, and that constraint is, when you unpack it, exactly that these fi's vanish. Okay, so an m jet is some data subject to some constraints, and therefore we can parameterize it by points of an algebraic variety, this spectrum here. So that's it. So computing the m jet of something that's given in terms of equations is nothing more than making these substitutions, expanding, collecting terms, and reading off some more equations. Okay, Any questions about that part? Maybe I'll do an example that's come up in this seminar just to make that more precise. Right, so let's consider the equation whose vanishing set is the set of true parameters for a 2 hidden node, 1 hidden layer, bias-free 10H neural network, which is this equation here. So how do I compute the jet schemes of this object? Well, I replace each variable by a kind of collection that looks like this. If I want to compute the second jet scheme, then I replace A by this, and similarly B by this, and so on with C and D. And then I just substitute. So let me call this A of T, I guess, B of T. So f of AT, BT, CT, DT, well, that's going to be A0 plus A1T plus A2T squared, B0 plus B1T plus B2T squared, plus same thing for C, same thing for D. Can you excuse me for just 1 second? I'll be back. Right, I'm back. So you make that substitution for CT and DT, and then you've got a square and you've got the other term. Okay, so you can see what's going to happen when you expand that out, right? You'll get A0, B0 plus C0, D0 plus terms of higher order in T squared, and the same in the other term. And when you expand all that out, you're going to get the original thing, F, in A0, B0, C0, and D0, plus some stuff times T, plus so on. This equation here, which is your original equation, will be F0. It's just, it's F, but in these new zero versions of the variables. And then you've got some other polynomial here in the AIs and BIs and CIs and DIs, and that's F1. And okay, then you have an order 2 thing. And then you have higher order terms, but you don't care about those. That's F2. And then, okay, so if we let X be the vanishing set of F, the second jet scheme is going to be R in A0, A1, A2, and so on with B, C, and D, modulo these 3 equations. Spec. Or what's the same? It's the vanishing set of those 3 equations inside, what's that? R to the 12. Right, so in practice, computing these jet schemes is maybe a bit laborious, but it's not anything complicated. Okay, let me look at the time. Okay, yeah, let's pause here for questions, and then I'll do some more foundational stuff. So I want to tell you what the symmetric algebra is. I want to introduce how to think about points as K-algebra homomorphisms, and how to use Taylor series expansions to talk about tangent vectors. And no, there was no reason to go to second order. It was just to go to first order would be kind of, well, In fact, I didn't really do anything, right? Since I didn't expand the brackets or actually do any work, that derivation I just gave in the example would have been essentially the same if I'd done third order or nth order. So there was no significance to second order. Right.
Is it fair to call the A of t's, B of t's, C of t parametrizing? So t is parametrizing an arc near A0, B0, C0?
Yeah, that's right.
Okay. I can't figure out what's the significance of having. So that's a function into. So,
yeah, think about it. Think about the arc. So if you fix a point A0, B0, C0, D0, then like imagine t to be a very small number. You think about t as being epsilon.
mm-hmm.
So as you vary t from minus epsilon to epsilon, you're tracing out a little path that goes through A0, B0, C0, D0.
So I can see why we need the constraint of f capital F0 being 0. That means that we are on the variety. But why do we want like higher order derivative to vanish?
Yeah, good question.
On the variety?
Hopefully that's what the discussion in a moment will clarify. But to give the short answer, if you look at on the left-hand board here, the blue tangent vector to x, it lies on x, right? That's a constraint. And the constraint is that it's dot product with, suppose x is the vanishing set of f as it is on this page, right? And the constraint for the blue line to be a tangent vector to x and not just a tangent vector to that point in K3 is that that blue line is orthogonal to the gradient of f. Right, so you have some constraint, which is this dot product is 0. Right? And this constraint is exactly one of the constraints that would be imposed by f1. In fact, it's the only constraint.
Okay.
So two jets, then you can ask, well, what are the constraints imposed by the equation f2? That's more interesting, and that's got to do with second order information in f, and we'll see the Hessian appear in the constraint f2. But the first order, it's simply saying that yes, the vector has to be at a point that's actually in the variety where f0 vanishes, and the additional data, which is telling you the tangent vector itself, needs to be orthogonal to the gradient.
Right. Okay. Thanks.
Cool. Okay, let's move over. So this is a discussion of a fairly advanced topic, jet schemes, and at the same time some elementary topics. Hopefully it's useful for those of you who haven't thought much about algebraic geometry. I'm going to say a little bit about the symmetric algebra, which is one way of thinking about the polynomial ring, just because I'll be talking, the way I'll discuss things makes heavy use of the universal property of the symmetric algebra. So I feel like it doesn't hurt to say in 2 minutes or so what this is. So let K be a field and V a vector space. Then the symmetric algebra of V over K is, well, I take the following direct sum. This is a tensor, so I tensor V with itself 2 times, 3 times, and so on. And then I take the direct sum of all of those. That's an algebra called the tensor algebra, where I multiply tensors by just concatenating them. So in this numerator here, I have things like A tensor B, and I multiply A tensor B with C by just forming the tensor A tensor B tensor C. You have to check that's well defined and so on, but it is, and makes an associative algebra, the tensor algebra, which is not commutative. But inside that non-associative but unital algebra, you can, sorry, non-associative. It's not commutative. I hope I said that right the first time. It's a non-commutative but associative and unital K algebra. And within that non-commutative algebra, I can mod out by the two-sided ideal generated by these pairs. Right, A tensor B and B tensor A are different things in general in the tensor algebra, but I can mod out by the two-sided ideal generated by all such pairs. That quotient, which a priori is just another associative algebra, is in fact a commutative algebra, and it's called the symmetric algebra. Okay, so that's a K algebra, commutative K algebra. Lemma, if V has a basis, so V is finite dimensional and has a basis E1 through En, then the symmetric algebra on V is isomorphic to the polynomial ring in n variables. We might as well call the variables E1 through En. And the correspondence here is between, in the obvious sort of way, EI maps to EI, and for example, EI tensor EJ, the equivalence class of that in that quotient is just the product EI EJ. All right. So I've already invoked the universal property of the polynomial ring, which is another way of saying the universal property of the symmetric algebra. So let me state it. Let me think for a moment if I actually need it. Yeah, I might as well. Okay, so lemma. So this is another way of circling back to justify why you should believe that something like n-jets are classified by K-algebra homomorphisms into that funny quotient kt modulo t to the n plus 1. Right? So let V be a vector space, A a commutative algebra, K-algebra. If phi from V to A is, just a second. Is K linear? There exists a unique K-algebra morphism capital Phi from the symmetric algebra of V to A, making the diagram V. So V obviously sits inside the symmetric algebra of V. Right? There's a map from V to here which just sends V, a vector, to the equivalence class in the quotient of V itself, where you sort of stick V in that factor there. Okay, so what this statement is saying is that any K-algebra homomorphism out of V can be lifted to the symmetric algebra. And that's pretty clear, because if you can map vectors in V to A, and inside A you can multiply things, then if I give you anything in the symmetric algebra, well, anything in the symmetric algebra is some tensor, and tensors can be obtained by multiplying. So anything in the symmetric algebra you can just get by multiplying together stuff in V, right? So for example, if I want to take A tensor B tensor C, A, B, and C vectors in V, well, that's just A times B times C. In the vector space V, I can't necessarily multiply things, but in the symmetric algebra, I can always multiply vectors in V to get other things in the symmetric algebra. And so, for example, if I take phi of A tensor B tensor C, or more precisely its equivalence class in the quotient, then, well, that's a product of A with B with C. Phi is a K-algebra homomorphism, so that has to send that to phi of A times phi of B times phi of C. But when I evaluate capital Phi on vectors in V, I should just get phi of them. So this is phi of A times phi of B times phi of C. And you can turn this into an actual definition of capital Phi. Okay. So this is just similar to knowing that if two linear transformations agree on a basis, they're equal, right? Phi preserves the structure of multiplication, so it's determined to whatever it does to generators. The vectors in V are generators, and on the vectors in V, capital Phi agrees with lowercase phi. Okay, so the one way to say that is that K-algebra homomorphisms out of the symmetric algebra are in bijection with K-linear maps from V to A for any commutative algebra A. I'm just going to pause for a sec to recharge my Apple Pencil. All right. So let's see. I now want to, or maybe I'll write one more thing and then invite you to think about this a little. So, example. Let's take A to be the field as a K-algebra, and take, instead of V, V star. So V star means the K-linear dual. Then K-algebra homomorphisms from sim V star to K are what?
Is that the double dual?
That's right. And the double dual is...
Homomorphic to V.
That's right. I guess I didn't say V was finite dimensional, but that was what I meant, yeah. So if I use the above bijection, that's hom K V star V, V star K, which is V double star, which is canonically isomorphic to V, if V is finite dimensional. All right. So this is a way of introducing the dictionary between sort of geometry and algebra, because we see here how a point of V, so think about V as being affine n space, so I take a point, P, corresponds in this canonical way to a K-algebra homomorphism, which I'm going to call phi P. What is that homomorphism? Phi P of F is what?
F of P?
Mm-hmm. Well, we have to, I suppose we have to explain what it means to evaluate f in the symmetric algebra on a point, as it stands, the elements of the symmetric algebra are just some equivalence classes of tensors, but we can think about them as functions on V. Well, the things in V star are clearly functions on V by definition, right? They're linear functions on V. And if I multiply linear functions with other linear functions, well, I can just multiply them as functions, right? And actually that's compatible with the multiplication on the symmetric algebra. So maybe I'll say it like this. Sim V star is a sub-ring of just functions on V. If I run out of battery. Oh no. I'll just say functions from V to K. Where you make that set of functions from V to K a ring by just pointwise multiplication in the usual way. And you can identify sim V star with a sub-ring of that. So the rule that we have for multiplication of these equivalence classes of tensors is compatible with just thinking about things in sim V star as functions. So sim V star is the coordinate ring of functions, of algebraic functions on V. Thinking of V as a variety, these are the polynomial functions on V. And phi p is the K-algebra homomorphism that takes a polynomial function and evaluates it at the point P. Okay, so the dictionary between points of a space, P and V, and K-algebra homomorphisms is that P corresponds to evaluation at P. Now, that's meant not to be very profound seeming, but now the cool trick is that if you think about a simple thing in a sophisticated way, maybe there's a way of getting something for free. So now I'm just going to replace A, or rather K, by a more interesting algebra. Namely KT modulo T squared. And that's got a ring of Joule numbers. But I need to let my pencil charge for a minute. Maybe you can think about it ahead of time. You can do this calculation as well as I can. So using the first isomorphism, I'll call it star. Using star, what happens if we take A to be the K-algebra KT modulo T squared? It's a two-dimensional vector space equipped with a multiplication where T squared is 0. So let's do it on the next board. Okay, so as a vector space that's got a basis which is 1 and t, and the multiplication rule is that t squared is 0. So let's compute. What happens when I take K-algebra homomorphisms from sim V star to A? Well, that's by star. That's V, comma A. And here I'm just taking K-linear maps. I don't care that A has a multiplication, right? I'm just taking K-linear maps, V star, right? Okay. So that means I'm taking k-linear maps from V star to k direct sum kt. Now if I take k-linear maps from some vector space to a direct sum of two things, that's just kind of like a matrix with two rows, right? A linear transformation to k plus kt is just two linear transformations, one to k and one to kt. Right? Just take the two rows of the matrix separately. So that's just the same thing as giving a k-linear transformation from V star to k. And yeah, I'm fighting the battery here. V star to kt. This is just a one-dimensional vector space that has a basis t, right? So I'm just going to drop the t because it's really just a one-dimensional vector space. But that's just two copies of V star, V double star rather. Okay, so that's V plus V. What are we supposed to make of that? So a k-algebra homomorphism from sim V star to this larger algebra is really 2 points in V. Now what we're going to do in a moment is trace through this isomorphism to see what a pair of points, P comma Q in V plus V, what k-algebra homomorphism they correspond to. But you might also be able to guess. So let me take P and Q here, and I think I have some notes I'll circulate. I just want to get the notation consistent. I think this is what I call psi PQ, yeah. Okay. So psi PQ has to take in a function f, and has to give you a vector in A. So it has to give you two scalars, right? Because that's what a vector in A is. One scalar which goes in the first spot and another scalar which goes in the second spot, sort of the coefficient of the t. Now it's a little, there is a way of explaining this without choosing coordinates, but maybe just for the sake of time, I'll now choose coordinates and explain how to think about it in terms of those coordinates, just because it's maybe a more familiar way of thinking about it. So let's do that. So to understand what this corresponding k-algebra homomorphism is, let's choose coordinates. So choose a basis. V is finite dimensional in all this. For V. Then I have a dual basis, the EI stars. And those are vectors in V star. So those xi's are a basis for V star. So if you like, sim V star is the polynomial ring in x1 through xn. It doesn't matter too much for us that you can think about it that way. Oh man. Okay. Apple Pencil has died. Okay, so what I'm going to do is well, psi PQ, whatever it is, so we're picking P and Q, and then under this chain of bijections we believe in, we get a psi PQ, but we don't know what it does. But whatever it does, it's determined by what it does to the generators, as I said earlier, right? If you have a morphism of k-algebras out of a polynomial ring, or this sim V star, then it's determined by what it does to the xi's. So that's the data in this object, right? So psi pq is determined by some numbers. So let me take psi pq and evaluate it on xi. That's some vector in A, so it looks like pi plus qit for some scalars pi and qi. Right? Define pi and qi to be those coefficients. All right, now coming back to Matt's earlier comment, let's talk about the Taylor series expansion of an f. So given f in sim v star, or if you like in the polynomial ring, we can consider its Taylor series expansion. We don't have to use limits and that kind of calculus to do the Taylor series expansion. It works perfectly fine algebraically. So the Taylor series expansion in n variables is the following. That's an I. So I'm doing the Taylor series expansion at the point P. You'll see why. Where P is defined, well, yeah, maybe now is the point to connect PIs, the PIs to the P. Yeah, so let's do that. So let me go back to this board here. Let's follow through how we get, what's the connection between the P that we had here and the psi. Okay. So we start with psi pq. How do we get to hom v star a? Well, we just restrict to v star, the copy of v star inside sim v star. The next line doesn't do anything. The line after that just splits this into a pair, which is psi pq restricted to v star and take the coefficient of 1. And then the second part is I take the coefficient of t, and then I get the isomorphism from v double star to v. And the way that works is, well, if I take pq, then this here has to just be, I take a functional and I evaluate it at p. So this is just evaluation of a linear functional at p. So if you track that through, you'll see that you'll see that these here, well, yeah, I guess what I'm sketching, and maybe I'll just leave it at a sketch, is that this isn't, I guess, as I said it earlier, not a definition, right? It's an observation that if you evaluate psi pq, this k-algebra homomorphism corresponding to the pair pq at the generator xi, you get pi plus qit, where these are this is the expansion of P, the point in V. It has an expansion in the basis. And the coefficients are exactly these numbers that show up here. So that's, if you just follow through this chain of isomorphisms, you'll observe that. So the thing I really want to argue for is, well, that's fine. We know what psi pq does to a generator. It gives us this expression. But what does it do to a general polynomial? And that's what I'm computing on the right-hand board here. Okay, so I take a Taylor series expansion of f, and then I apply psi pq to it. This is a K-algebra homomorphism. So in particular, it's linear. Let me just write this. Same expression. I'm just going to simplify it. This is just a number. And then I've got psi pq of this stuff. So what does psi pq do to all that? Well, it's a K-algebra homomorphism, right? So I can, this part here becomes, I can take the psi inside, and it's psi pq of x1 minus p1 to the I1 dot dot dot. It's psi pq of xn minus pn to the In. But psi pq of x1 is just p1 plus q1t. And then I'm subtracting p1. So this is the sum over this multi-index 1 over this exponential term, and then this derivative. And then I've got, as I just said, psi pq x1 minus p1 is just q1t. All right, so now this calculation's just for tangent vectors. That's just what we're about to discover. But the same calculation tells you what higher jets are talking about, right? So this is something we'll revisit, but the core of the idea is already present here. Because, well, what's this? This is q1 to the I1 dot 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 qn to the In t to the sum over all the i's. Let's go with J, I guess. But the codomain of the psi is in A. And in A, anything that has a power of t above 1 is 0. So most of these sums, I mean, this is a finite sum because the polynomial only has finitely many non-zero derivatives. Most of these sums are 0. So which ones actually survive? Well, a multi-index I has a surviving contribution to this sum exactly when none of the ij's are non-zero, so they're just all 0, in which case I get t to the 0, or exactly one spot has a 1 in it and the rest are 0. Okay, so you can see hopefully what this sum has to be. So I get the case where the multi-index I is just all 0, so there's no derivative, and I'm just evaluating f at p. And then the rest of it is just doesn't do anything, right? All the i's are 0, so this is just a bunch of 1s times t to the 0. And then I get all the contributions from where exactly one index in this multi-index I underline is 1 and the rest are 0. And that is just the sum over which position is non-zero, and then I'll get a derivative exactly in that position of f evaluated at p, and then exactly one of the q's will have will be to the power 1, and the rest will be to the power 0, and that will be qj. Okay, so this is fp plus the gradient of f at p taking the dot product with Q. Okay, so what we've discovered is that... Oh yeah, thank you. T, yeah, that's right. Yep. Okay, we didn't put in derivatives here anywhere, right? So I introduced the Taylor series expansion in order to compute this psi, but even if I didn't know what a derivative was, I would have just invented it by just thinking about this k-algebra kt modulo t squared. And following this canonical bijection from a pair PQ, I get this psi PQ, which both evaluates f at p and takes the derivatives of f at p and takes the dot product with q. So, well, that's the directional derivative, right? That gradient dot with q is the directional derivative in the direction q. So the upshot is that this psi PQ map is a tangent vector at the point P in the direction Q. That's what this pair PQ means. It's a tangent vector based at P in the direction Q. Okay, so that's what a one-jet is. To define a two-jet, you take a k-algebra homomorphism. So a two-jet on V at a point P is a k-algebra homomorphism from sim V star to kt modulo t cubed. And then we can think about, by doing a similar calculation, what the higher order terms mean and what the information in them is. But we'll do that at some point, maybe not next week. We'll see what we want to do next week. But that's the next stage, to talk about two jets and higher jets and how they fit together to form the jet schemes. But the underlying calculations are more or less determined by what we just did. Right, so I'll stop there and take questions. Yep, see you, Matt.
I think I might have asked you this before, Dan, but do you have a recommended reference for jet schemes?
Yeah, I probably don't have a better answer now than I did that time. Yeah, there's some references. I don't know a textbook. It appears in some textbooks. So, for example, you can look at algebraic curves and vertex algebras by Bensby and who's the other author on that book? Frankel and Bensby. That has a section which treats jet schemes. It's at a quite high level. There are some papers with better kind of more elementary introductions, and I'll post some of those in the Discord.
Cool. Thanks.
So the hope, to come back to the relation to learning theory at the beginning, I'm hopeful that, so in the cases that are treated by information geometry, so the regular case, we know how to think about higher order terms in the asymptotic expansion of the free energy in terms of geometric structure. And it seems like in the singular case you should be able to do something similar, but in the regular case it's basically in the language of jet bundles already. Maybe that's so in the Bala Subramanian paper it's not stated that way, but you could state it that way. And I don't see any reason why you couldn't expect a similar kind of theory in terms of jet schemes in the singular case, which generalizes that. As far as I know, that hasn't been done. But so the reason to maybe be interested in that is, so far most of the discussion, the relation of algebraic geometry to SLT is via the resolution of singularities. But as I said at the beginning, some of that information is already in the JET scheme, and maybe it's actually there in a better way, in the sense that the JET scheme is canonical and the resolution is not. So there's probably, one would have to guess, an important role for JET schemes in SLT, which is so far unexplored. Any other questions?
What is the difference between jet bundle and jet scheme? As in, other than the conceptually, other than the obvious.
They're really not the same thing. They're different notions of jet, unfortunately. So they have a very similar sounding name, but the question is, I wrote up these bullet ends before, right? Like, what are the infinitesimal models that you're considering mapping into your space? And for differential geometers, it's a different kind of the local objects they're considering are not the same. So it wouldn't be. So here we're only considering things like kt modulo t squared, or t to the cubed, or t to the n. The differential geometer's jet bundle is more like you would also allow kuv modulo u squared comma v squared. So it's kind of a achieves similar things, but in some sense quite different.
So something like not just arc, but infinitesimal surfaces and volumes and so on.
That's right. Yeah, exactly. Yeah.
So more information.
You would think so. Yeah, that's right. So the theory of jet bundles is really about differential equations. So it's sort of like got a similar aim. You're probing your space in some infinitesimal way, but the objects you're probing it with are more general. And so you get a more general theory, but it's kind of, in some sense, going in a different direction, because you care about jet bundles are defined for manifolds, so there's no singularities to worry about. Here you're probing, you don't care about jet schemes of things that aren't singular, you'll just get back some boring thing. You don't care. So they have some similarity in their name and the kind of idea of probing your space with some infinitesimal gadgets and parameterizing all the ways you could map them in and making a space out of that. But they're being used for somewhat different purposes. In the case of jet bundles, to basically set up a language to talk about differential equations as maps, and here to talk about arcs that are probing the structure of singularities. So I'm not an expert in either theory, but they seem to be doing, and I'm not sure there's a lot of useful overlap. There may be.
Right. I'm going to ask a sort of aggressive sounding question. So, what's the what do we gain by having this so the purpose is to study sort of singularity, so near infinitesimally near W0. So what does the structure of the kind of the algebra here tells us about something that we can having just a local chart and have a local sort of chart representation of our functions. What does that by this, I guess. What does the structure of the algebra tell us?
Yeah.
Sorry, that's a very poorly worded question. Like, I guess it's kind of the general question between like, what's the difference between sort of an algebraic geometry point of view versus just straight up differential geometry point of view.
Yeah, I think I understand the question.
Okay.
So at the level of, suppose we take one hidden layer tanh networks, then we can write down the equations that define these M jet schemes for all M. Maybe. I mean, there's some terrible polynomials. They exist, but okay, maybe we don't want to compute them. So what if we could? What does that even tell us? I'm not sure it does tell us much, to be honest, to just compute those. In the same way that, you can go and compute the RLCTs, but what do those numbers tell you? What we're interested in, I think, is what we can say theoretically more than computing things. So we know in some cases that, as I was saying earlier, the irreducible components of the pre-image under the map from the arc scheme to X correspond to the essential exceptional divisors of the resolution. Now maybe that means we can say something about what those components mean, right? Because maybe we find a way of relating this these x's or the behavior of kn minus k near the set of true parameters. Maybe we find a way of saying something about that in terms of those components of the arc scheme in a way that's maybe less tractable when we talk about the resolution. I don't really know, but so the answer to your question is I don't know. So I'm just kind of... the resolution is not a canonical object, right? It's go over here, do a blow up, go over here, do a blow up. The arc scheme is not like that, right? The points of the jet schemes are really very simple objects that are clearly defined, right? They're truncations of arcs that pass through your variety. So given that it's a canonical object, it seems more tractable that maybe we can use it to say something, rather than just kind of saying a resolution exists out there and, whatever it is, we can do something with it and compute a number that's independent of the choices. So that's the idea.
Right, that kind of makes sense. I actually don't have a good picture of how resolution could be different. Like, is it different in some kind of global manner, but like locally around each point it's somehow similar? As in...
Oh no, not at all. There's no obvious... I mean, that's a very difficult question. So you can say something in some cases, but in general they're just different.
Right. But they all produce a normal crossing form for the variety.
And the number you compute from them is independent of the choices, but the resolutions themselves have no obvious relation.
Right. So in sort of our SRT settings, it's like the Ks are different, the H's are different, but RLCT is the same.
I'm not sure what you mean by the Ks are different.
So the Ks being the normal crossing.
Oh, the little Ks. Yeah, that's right. Little Ks and little H's. Yeah, that's right. They could be just completely different. The geometry, you could have completely different sets of essential coordinates, and it's just like some miracle that the quotients are equal.
Okay, and
so what it means is that anytime we're talking about, like, we're tempted to assign some meaning to the resolution, right? Like it's saying something about the original learning process. But that's really a mistake, because our resolution is, some of that information is real in the sense that it's intrinsic to our original problem, and some of it is just junk that's there because we made some choices and not others in the blow-up process. And And the idea, Nash's idea, which is like not completely worked out, right? There's still a lot of conjectures in this area, but the conceptual idea of the arc scheme is that it's the stuff in the resolution that's independent of your choices. At least for some nice x's.
Right. Does this have anything to do with the other sort of canonicalization of resolution, like the minimal resolution or something like that?
Yeah, good question. For cases like surfaces where a minimal resolution exists, I guess you would expect to be able to find some closer relation between the jet schemes or the arc scheme and the minimal resolution. I'm not enough of an expert to know what that relation is. I think in the case of like quotient singularities, I think there is some understanding of how the arc scheme of say this quotient surface singularity, how to compute that, but I don't remember how that goes. So, yeah,
okay.
Good question.
So the way to tackle this would be sort of understand the case Nash was investigating in digital toric setting.
Yeah, so that's right. So I don't understand the proofs. I haven't even looked at the literature, but I've seen the statement that for toric varieties, this conjecture of Nash's, or the Nash problem, is true. So that's a bijection. So yeah, that might be interesting. At least that should cover the case where you have a zero true parameter for tanh neural networks. So maybe that's interesting. Yeah.
Right.
I gotta go. Thanks, guys.